Hello everyone, today we are here in Reactor and today we are going to perform an experiment to study the kinetics of ethyl acetate and sodium hydroxide in an isothermal semi-batch reactor. Now let's move on to our experimental setup.
In the experimental setup, we can see that we have a rotameter, a storage tank, an overhead tank, a control panel, a CSTR and an agitator. So basically, this storage tank here contains ethyl acetate. This ethyl acetate is fed to the reactor using a pump. Now, we can see that we have an overhead tank. So what is the purpose of this overhead tank? The main purpose of this overhead tank is when the rotameter is set to 0, the ethyl acetate flows from the storage tank to the overhead tank and then comes back to the storage tank. We can see that we have a rotameter here. The main purpose of this rotameter is to set the flow rate of the reactants. Now, the reactor used in this experiment is a CSTR, a continuously stirred tank reactor. This continuously stirred tank reactor will be surrounded by a water bath. The water bath contains a heating coil. This heating coil will be set to a certain temperature. The main reason for doing this is such that in order that the water bath maintains its temperature throughout the reaction, we want the water bath to be maintained at a certain temperature. For this, we will use a heating coil and we will set the temperature of heating coil, and now we can see that we have an agitator here. This agitator is started as soon as the reactants gets filled inside the CSTR. Now we have a control panel here. In this we have a switch on and off. When we switch on this, the main indicator gets light up. We also have a heater switch, we also have a pump switch, and we also have an agitator switch. To maintain the speed of the agitator, we have a knob present here. When we shift the knob, we can change the speed of the agitator. So, this is all about the experimental setup of this experiment. Thank you.
Let's start the experiment. Switch on the main. Then let's start the heater and set the temperature at 45 degrees. Switch on the pump and the ethyl acetate start flowing in the pipe. We can control the flow rate of ethyl acetate in a reactor by using the rotameter. The initial flow rate of the rotameter should be 0. Now we will fill 1.2 liter of 0.1 normal annual solution in the reactor using the measuring cylinder. Now we will set the flow rate of ethyl acetate at 0.5 lph.
As soon as the ethyl acetate starts going into the reactor, we switch on the agitator button which is given on the control panel and set the speed of the agitator at 80 rpm. Meanwhile, you start the experiment, have one of your group members serially arrange the conical flasks which are containing 20 ml of 0.1 normal HCl and 2-3 drops of phenolphthalein indicator. We set the timer and after the 3 minutes since we start the flow rate of ethyl acetate, we take 10 ml sample from the CSTR using a syringe and add it into the first conical flask. while you are taking the sample, have one of your group member titrate the sample against zero point 0.1 normal NaOH and note down the burette endpoint reading in the observation table prepared prior to the experiment.
After completion of the experiment, we drain the reactor by using one given below, but you should not drain the water.
In the similar way, we perform the experiment for the flow rates of 10 lbs and 12.5 lbs. This concludes our experiment. Thank you.
Hello everyone, my name is Nikhil Tiwari and this video is regarding the experiment of isothermal semi-batch reactor which we performed at CRE laboratory. Now this section of video will cover the introduction and theory part for second order reaction carried out in an isothermal semi-batch reactor. Now here isothermal conditions are maintained to eliminate any change in rate constant of the reaction due to the change of surrounding temperature. Now, in chemical engineering, it is very important to study the reaction mechanism and kinetics of the reaction to design any reactor. It is very crucial for designing the reactors. Now, in this experiment, we are studying kinetics of reaction between sodium hydroxide and ethyl acetate, which is a classical example of a saponification reaction. This process is widely studied in chemical kinetics because it is a well understood second order reaction. Coming to the reaction mechanism of this reaction occurs in an aqueous medium and involves a nucleophilic attack of the hydroxide ions on the carbonyl carbon of ethyl acetates, leading to the cleavage of the ester bond, which yields us the product sodium acetate and ethanol. Now, this is a second order reaction. This is governed by the second order rate law, which is given by rate equal to K, which is a rate constant into concentration of sodium hydroxide into concentration of ethyl acetate. Now we will look into the derivation of performance equation and calculation in the later part of the video. Now let us study some basic feature and working principle of a semi-batch reactor. A semi-batch reactor is a type of reactor that combines features of both batch and continuous reactor. In a semi-batch reactor, one reactant is fed continuously into the reactor while the other reactant is present in the reactor initially. In this schematic diagram, we can see that reactant 1 and reactant 2 are fed gradually while the reactor is initially charged with some other reactant. In our case, we initially charge the reactor with sodium hydroxide and gradually add the ethyl acetate by adjusting the flow rate using rotameter. Now, a stirrer is provided for proper agitation and mixing and which gives us control over the reaction rate by ensuring homogeneity in the reactor. Now a coolant system is provided for the temperature management. A heating or cooling system in reactor is used to handle exothermic or endothermic reaction efficiently. A vent is provided to remove any of the gas produced in the reactor to avoid pressure buildup in the reactor, which will eventually lead to the explosion of the reactor. Now, this control addition allows us improved management of reaction rate. The control addition of feed gives us better control over the concentration and which will eventually improve management of reaction rate. Now it is also gives us better heat dissipation for exothermic reaction. We already know that a large amount of heat is evolved in exothermic reaction, and if a large amount of reactant is initially used, a large amount of heat will be evolved, which will lead to a high reach temperature in the reactor, which we are not desiring. Therefore, by gradually adding the amount of feed, the amount of heat evolved can be controlled and can be easily put off by a cooling jacket system provided in the reactor. Now, it also gives us high conversion rates by optimizing reactant concentration. Now, in semi-batch reactor, control feed of the reactant avoids the overloading of reactant, which eventually reduces the likelihood of undesired side reaction and gives higher conversion rate. Now, here we can see the schematic diagram of any semi-batch reactor in industry. It is featured with an agitator, a manhole, a liquid import from where the reactant will be fed, drive shaft protection, liquid outlet for the product outlet by the reactor, a jacket is provided for thermal management, and this tank body is made up of stainless steel and support legs are provided to support the reactor. Now, by concluding this, we can say that an isothermal semi-batch reactor is demonstrates utility of such reactors in handling reaction rate with sensitive kinetics. This controlled addition of reactant enables better thermal management, higher safety, and efficient reaction progress. This approach is particularly valuable in industrial chemical process where precision and safety are paramount.
Hello everyone, myself Ranjit Kumar. In this video, I am going to discuss design equation of semi-batch reactor. Let us consider the following two component reaction taking place in the reactor, that is A plus B gives R. In a semi-batch reactor, the composition and the volume both varies with time. This is the key point in a semi-batch reactor. The notations for the reactor are as follow. Here we can see in semi-batch reactor B is already filled and amount of B is V naught and A is added slowly with the volumetric flow rate is mu naught and initial concentration Ca naught. Now we make the balances. First we balance total mass for the reactor, that is input is equal to output plus accumulation. Say this is equation 1. Now we can see mass input to the reactor will be rho times mu naught, that is rho is the density of a stream coming into the reactor and V naught is the volumetric flow rate. So mass input will be rho V naught. As we can see, there is no output, so mass output from the reactor will be 0. And accumulation of mass in the reactor we can write like d rho V upon dt. Here rho is the density of uh, material in the reactor. Here we assume density coming through the stream and density in the reactor is same, and V is the volume at time t. So accumulation of mass in the reactor is d rho v upon dt. Putting all these values in equation 1, we get rho v naught is equal to 0 plus d rho v upon dt. Just rearranging, we get d rho v upon dt is equal to rho v naught. This is equation 2. Now if we take rho is equal to constant, then equation 2 becomes dv by dt is equal to v naught. Say this is equation 3. Integrating equation 3 with initial condition, that is at t is equal to 0, v is equal to v naught. Rearranging equation 3, we get it is integration of dv from v naught to v in right hand side, and in left we get integration from 0 to v naught mu naught dt. After solving this, we get v is equal to v naught plus mu naught into t. This gives the variation of v with respect to time. Now we will make material balances, that is input is equal to output plus disappearance by reaction plus accumulation. Say this is equation 5. So for A, material balance is input of A will be V naught Ca, that will be equal to Fa naught. As we know, output is equal to 0. Disappearance of A by reaction will be minus Ra into volume. Accumulation of A will be dVca upon dt. Putting all these in material balance equation, that is equation 5, we get V naught Ca is equal to 0 plus minus Ra into V plus dVca upon dt. Since both Ca and V varies with time, we can write, we know mu naught Ca is equal to minus Ra into V, and differentiating this term by product rule, keeping V is equal to constant dCa upon dt plus keeping Ca constant dV by dt. So term will be mu naught Ca naught is equal to minus Ra into V dCa upon dt plus Ca dV by dt. After solving 2 to 3 step, we get dCa upon dt will be is equal to Ra plus mu naught Ca naught minus Ca upon V. This is the design equation for component A. Similarly, for B, we make material balance. As we can see, input of B is 0 because B is already filled in the reactor. So input rate of B will be 0, and obviously it is a semi-batch, so output will be 0. Disappearance of B will be minus RB into V, and accumulation will be dCV V upon dt. Now putting all these term in material balance equation, we get this, that is input is equal to 0 and output 0. Disappearance will be minus RBV and accumulation dCV upon dt. We just after rearranging this, we get dCV upon dt will be RV into V, and after differentiating by product rule, we get this term. And now putting the value dV by dt is equal to mu naught from equation 3. From equation 3 in above equation, so we get Cv mu naught plus V dCV upon dt is equal to RBV. Rearranging above equation, we get dCB upon dt is equal to RB minus mu naught Cv. This is the design equation for component B. So overall design equation for semi-batch reactor we can write like for component A, dCa upon dt is equal to Ra plus mu naught Ca naught minus C upon V, and for B dCV upon dt will be Rb minus mu naught upon Cv upon V. So this is the performance equation for this is the performance this is the performance equation for semi batch reactor. So that's it, that is all.
Hello, myself Shobit Kumar Singh. I am going to explain the sample calculation of isothermal semi-batch reactor. First, we will see the reaction between NaOH and ethyl acetate, and here are the products of the reaction. Now, as we know, the volume of reactor mixture is changing with time. So, Ca will be moles of A divided by volume, and Cb will be Ft Cb naught minus Na naught minus Nt, where V is V naught plus Ft. Now we will go at the transient component balance for component A, which will be minus dNA by dt will be KVCA Now minus dNA by dt is basically Ra into V, which is equals to KVCA. Now after simplifying, we will get KNAF into FT naught minus V Ca naught minus Na whole divided by V, which is equals to V naught plus Ft. This is our equation number 1. This equation can be solved using Runge-Kutta method, which is basically xn plus 1 is equals to xn plus 1 by 6 k1 plus 2 k2 plus 2 k3 plus k4. After solving this equation by Runge-Kutta method, we will finally get k is equals to minus dNA by dt into V naught plus Ft upon Na Ft Cb naught minus V Ca naught minus Na, and the unit of K will be liter per gram mole minute. Now I will discuss about the sample calculation. Here, first the given values will be discussed. Ca naught, which is 0.1, Cb naught, which is 0.1 normal, V naught, which is 1.2 liter, which is basically the initial NaOH volume. Now the volumetric flow rate of B is basically 10 liter per hour. We will convert it into 10 liter per minute. We will divide by 60. The time is given as 4 minutes, and the initial concentration of A is 0.12 moles. The reaction as discussed earlier is NaOH plus C3CO C2H5 gives basically C plus D. Now we will discuss about the number of moles of HCl remained, which is basically the initial minus reacted moles, which is given by 0.1 into 20 upon 1000 minus 10.9 into 0.1 upon 1000, which comes out to be 0.00091 gram mole. Okay, by reaction stoichiometry, we will get number of moles of A, which is NaOH, as 0.0091 gram mole, and concentration of A is given by Na by V, which can be calculated by here as 0.0091 into 1000 upon 10, which is converting by it into mole per liter, which comes out to be 0.091 mole per liter. Now conversion of A, which can be given by the formula X is equals to Ca naught minus Ca upon Ca naught, and after substituting the values here, we get 0.1 minus 0.091 upon 0. As discussed earlier, the value of K, we will substitute the values of above data here, and we get it as minus dNA by dt into 1.2 plus 0.1667 into 4 upon Na into 0.1667 into 4 into 0.1 minus bracket 1.2 into 0.1 minus Na. Now we will calculate the number of moles of A, which is given by the equation Na is equals to Na naught 1 minus Xa, and after substituting the values, we will get it as 0.12 into 1 minus 0.09 the final value of Na is 0.109 moles. Now we will find the change in magnitude of number of moles of A upon change in time, which is given by the equation Na minus Na naught upon T2 minus T1, which is equals to 0.1092 minus 0.1128 upon 4.2. We will get delta Na upon delta T as negative of 0.0018. Now we will substitute all the values in the equation of k to get the final value of k, which is given as minus of minus 0.0018 into 1.2 plus 0.1667 into 4 upon 0.109 into 0.111667 into 4 into 0.1 minus bracket of 1.2 into 0.1 minus 0.1091, and after substituting all the values we will get the final value of k as 0.5537.
Hello everyone. So far we have gone through the theory, derivations and calculations. So now we are looking to the results and analysis of isothermal semi-batch reactor experiment. After that, we will go for the discussion. We have calculated the value of y and x at different time intervals and the different flow rates. So by plotting the graph, we will get the value of k, that is reaction constant, rate constant at different flow rate. So we can see in the graph that we have plotted the data y versus x at a different flow rate. The blue line represents the flow rate at 7.5 lph, red line represents the flow rate at 10 lph, and yellow line represents the flow rate at 12.5 lph. So now what we can predict from this graph is that as the flow rate increases, the reaction time varies, indicating different kinetics at various flow rates. So we can see that as we increase the flow rate, the reaction kinetics changes. Like if the yellow line, the red line, and the blue line does not coincide each other. It lies one over another. It shows that the reaction kinetics changes as we increase the flow rate. So the reaction time does not, now coming to the second point, the reaction time does not increase linearly with the flow rate, suggesting that other factors such as mixing efficiency or mass transfer limitations may influence the reaction kinetics. We can see that the line is not linear. It has some sharp point like that is it is deviating from the linearity. But we can predict from this that there are other factors like mixing efficiency, mass transfer limitations may influence the reaction kinetics. Now coming to the effect of the rate constant, the observed rate constant increases with higher flow rates, indicating a possibly enhanced reaction rate or efficiency at increased flow rate condition. So what we can predict that as we increase the flow rate, the value of K is increasing. As we value of K increasing, so that is what it is said in the graph that the observed rate constant increases with higher flow rates, indicating a possibly enhanced reaction rate or efficiency. Now coming to the second point, the reaction rate value suggests that the reaction is more efficient at higher flow rates, but the efficiency gain decreases beyond a certain point. So we can predict from it that the reaction is fast at higher flow rates, but the efficiency of the reaction got decreases. That is, at higher as we increase the flow rate, At after a certain point, the efficiency, the conversion from our product will decreases. So there is a certain limit at which this system, this experiment can work with maximum efficiency. So now coming to the endpoint variability, the endpoint decreases with increasing flow rates, suggesting faster attainment of equilibrium or endpoint at higher flow rates. So we have seen in the table that as we increase the flow rate, the volume of sample taken to get the endpoint is decreasing. Like at 7.5 LPS, the volume taken is more as compared to 10 LPH or as compared to 12.5 LPH. So on increasing the flow rate, the time taken to attain the equilibrium decreases. Now, this variability indicates that reactor achieve steady state condition more quickly at higher flow rates, likely due to improved mixing and mass transfer. So the reason to attain higher, faster equilibrium or steady state is that due to improved mixing and mass transfer. So now coming to the discussion part, that is the impact of flow rate on reaction kinetics. The experiment shows that the flow rate significantly impacts the reaction kinetics. Yes, we have seen into the graph also that higher flow rates improve the reaction rate, but beyond a certain point, the benefit decreases. I have mentioned this point also that as we increase the flow rate beyond the at certain point, beyond that point, the flow rate efficiency, the efficiency of the reaction would decreases. That is, the conversion will be less. So this behavior is typically for semi-batch reactor, where the mixing efficiency and mass transfer rate plays a crucial role in determining the overall reaction rate. So now coming to the optimization of reaction condition. To optimize the reaction condition, it is essential to find a balance between the flow rate and the reaction time. Increasing the flow rate improves the reaction rate up to a point, but excessive flow rate may lead to the inefficient mixing and mass transfer. The optimal flow rate should be determined based on achieving the highest conversion efficiency while maintaining effective mixing and mass transfer. So we can see that as we increase the flow rate beyond certain point, the efficiency decreases. So to get the best outcome, we have to find a optimal flow rate at which the our efficiency will be maximum while maintaining the effective mixing and mass transfer also. So that will be our optimal flow rate. So reactor design and scale up. The findings from this experiment can inform the design and scale up of the reactor for industrial application. The findings what we got from the experiment can be helpful for industrial application like understanding the relationship between the flow rate and reaction kinetics helps in designing a reactor with better efficiency, maximum efficiency. On large scale operation, it may be necessary to incorporate additional mixing or mass transfer enhancements technique to achieve the desired reaction kinetics. Potential for further studies, we can say that it has a deep dive future which we can explore into. Like further studies could involve varying other parameters like temperature, pressure, catalyst concentration to gain a more comprehensive understanding of this reaction kinetics. In our experiment, we have kept the isothermal condition. So by varying other parameters like temperature, pressure, and catalyst, we could gain a more comprehensive understanding of the reaction kinetics in our isothermal semi-batch reactor. So thank you.
So far, we have covered the theory, derivation, and calculation for second order reaction in isothermal semi-batch reactor and have explained the experimental setup and procedure and have also discussed on results and conclusion derived from the experiment. So now in this video we are going to dive into application part of a isothermal semi-batch reactor in industries. Given here are the 5 fields where isothermal semi-batch reactor plays an important role to carry out reactions in controlled manner and yield high quality products. Starting with exothermic reaction, it is used to manage highly exothermic reaction by gradually adding one reactant to control the heat release and prevent thermal runaway, which ensures safety and avoids side reactions caused by the high temperature. Second one is selective reaction. So it enhances selectivity in multiple step reactions by controlling the concentration of the reactant, which helps favor the formation of desired products over unwanted byproducts. Third one is handling gas liquid reaction. It is suitable for reactions involving gas absorption into a liquid as it allows the controlled gas introduction to optimize the reaction rate. Fourth one is polymerization. It is ideal for polymerization process where temperature control and gradual addition of monomers are crucial to manage reaction kinetics and avoid gelation. It offers the gradual addition of monomers and initiators which help us to get the desired product. Fifth one is biochemical process. It is used in fermentation and enzymatic reactions where controlled feeding of substrate ensures optimal growth conditions for microorganisms or enzymes. Now, we will look into some actual industrial processes carried out using isothermal semi-batch reactor for the production. First one is in pharmaceutical industries. In pharmaceutical industries, production of active pharmaceutical ingredients, shortly called as APIs, are done. Here, API are the biologically active components of a drug that are responsible for its therapeutic effect. Now, here the process example taken is synthesis of aspirin, and if you look into reaction, it is a acetylation reaction between salicylic acid and acetic anhydride. If you look into purpose of ISBR, acetic anhydride is added gradually to salicylic acid to control the exothermic reaction by using the cooling jacket mechanism of the semi-batch reactor, and here isothermal condition maintained ensures higher purity and yield of aspirin by avoiding this side reaction. Second one, in chemical industries, production of nitrobenzene. Now, if you look into process example, nitration of benzene is done, and if you look into reaction, here benzene reacts with mixture of concentrated nitric acid, that is HNO3, and sulfuric acid, that is H2SO4, to form nitrobenzene. Now, nitrobenzene is a synthetic oily flammable liquid and it is used as a solvent in production of aniline dyes and drugs, which make it as a industrially important solvent. Here purpose of isothermal semi-batch reactor is like nitric acid is added incrementally to benzene in the presence of sulfuric acid to manage the highly exothermic reaction. Here constant temperature prevents the formation of unwanted dinitrobenzene. Third one is polymer industries. In polymer industries, emulsion polymerization reactions are done using semi-batch, isothermal semi-batch reactor. Here process example is styrene butadiene rubber production. If you look into reaction, it is a polymerization reaction between styrene and butadiene in a water emulsion. Now SBR, that is styrene butadiene rubber, is 25% styrene and 75% butadiene. It is primarily used for the production of car tires and also has other application in concrete repair and waterproofing. If you look into purpose of ISPR, monomers and initiators are fed gradually to maintain control over the molecular weight distribution And here heat generated during polymerization is efficiently removed by maintaining isothermal condition. The fourth one is fine chemical. In fine chemical, synthesis of dyes and pigments are done. If you look into process example, diazotization reaction is done here. If you look into the reaction, it is formation of diazonium salts from aromatic amines and sodium nitrite in the acidic condition. Now, diazonium salts are used in dyes and pigment industries, and it is very unstable and decomposes easily. Now, purpose of ISBR here is sodium nitrite solution is added dropwise to control the exothermic reaction and ensure stable diazonium salt formation. Now, as the diazonium salt are unstable, here isothermal conditions minimizes decomposition and side reaction, which reduces the instability of the diazonium salts. Now, so this concludes us that the ISBRs have unique ability to handle sensitive and controlled reaction, makes it an invaluable tool in industries where product quality and safety are the paramount. So here I conclude the video on isothermal semi-batch reactor and hope that you may have got insights on the experiment procedure, calculation, and also the application part of the isothermal semi-batch reactor.